So far, our discussion of dummy variables in regression models was confined to dummy independent variables. However, there are many important research questions in which the study variables are dependent variables or qualitative, like decision to accept a job offer, bankruptcy of the firm, buying a home, decision to go to school, decision to quit smoking, choice of commuting in public transport. For the econometric studies that concerned with these research issues, dependent variables are dummy variables. In this module, I am going to outline some of the major concepts in dummy dependent variables model. I am going to answer what are all the qualitative dependent variables model exist, what are all the special inference problems we may face in these models. So, let us go to the class. Now, let us see the basic concepts of the qualitative dependent variables model. The qualitative dependent variables model handle the study variables of the following kind. Study variables are dependent variables of the following kind: choice of brand, choosing brand A or choosing brand B, like Pepsi or Coca-Cola; choice of public transport versus private vehicles; labor force participation that involves work or leisure decision to give loans, either to sanction or to deny loans. All these dependent variables are qualitative in nature. They take two values. The two choice decision variables are called dichotomous or binary variables. The models involving these variables as dependent variables are called binary response or dichotomous or binary choice models. Dichotomous or binary variables would assume two values, namely 0 and 1. There are two approaches to the estimation of dichotomous or binary choice or binary response models. One approach is linear probability model, shortly called LPM. The other approach is LOGIT model. First, let us explain the linear probability model. In this model, the probability is regressed on the linear function of independent variables. This model is widely used. They were used widely during 1960s and 70s. So, simply the dummy variable di is equal to alpha plus beta xi plus ui. Di hat is the probability of occurrence of di is equal to 1. That is, the expected value of di is equal to probability of occurrence of di is equal to 1. Di hat is equal to alpha plus beta xi. The marginal value, that is beta, measures the change in probability in response to a unit change in independent variable. This model is simply estimated using OLS. The marginal coefficients t values, f and r square values are interpreted like we do in MLRM or SLRM. But this approach has got some problem. So, let us discuss about the problems of LPM. In the LPM, theoretical range of alpha plus beta xi is minus infinity to plus infinity, but logical range must be between 0 to 1, because it is a probability. Probability cannot exceed 1 and cannot go beyond 0, below 0 also. So, d hat the predicted probability does not lie, if the d hat, the predicted probability does not lie in the range 0 and 1, that will make the interpretation difficult and sometimes absurd. So, this is a real possibility that di may be out of bound most of the time. This, apart from this LPMs will also have heteroscedasticity problem, because this heteroscedasticity means the variance will tend to vary with the other variables, the independent variables, or it will be varying. The heteroscedasticity problem is another important issue in LPMs. Let us take the equation in the deviation form, the model in the deviation form. Di is equal to beta xi plus ui, that means ui is equal to di minus beta xi. If this is the case, for di is equal to 1, we will get ui 1 minus beta xi. The probability of d equal to 1 is beta xi, and if you put 0, then we will get minus beta xi, u is equal to minus beta xi. The probability of is 1 minus the probability of d equal to 1. So, this is 1 minus beta xi. So, given this values, we may calculate, they follow the binomial distribution, and so we may calculate the variance of ui. Variance of ui is equal to expectation of ui square, that is equal to 1 minus beta xi the whole square into beta xi plus minus beta xi the whole square into 1 minus beta xi. So, that is equal to, now actually we can take 1 minus beta xi into beta xi outside, inside we will have 1 minus beta xi plus beta xi, both will get cancelled, then will be left with 1. So, we will get beta xi into 1 minus beta xi, that is equal to di hat into 1 minus di hat. So, this is heterogeneous, actually. So, this is not a constant, and so the variance is not constant. So, if you apply WLS with square root of di into 1 minus di as weight, it may solve the problem of heteroscedasticity, but still the problem remains. There is no guarantee that di will be within the bounds of 0 and 1, and so most of the time it will be out of bound. So, this is the problem that cannot be rectified in this LPM. Let us take one example of an LPM model and how it is interpreted. Also, we have the problem, the statistical inference, relating to the statistical inference. The statistical inference have to be based on binomial distribution, not based on the normal distribution, because the ui is following binomial distribution or the normal distribution, however big the sample may be. Now, let us take one example of an LPM. This is a simple LPM model with one independent variable. This is a deny, means we are denying of loans, denial of loans as a function of debt payment divided by income, debt payment as a proportion of income. As we know, as the probability this debt payment proportion increases, there is a more chance of your loan getting denied, and so the denial and the P by I ratio is positively related, and so the sign is positive here. What does this coefficient indicate? This means 1 unit increase in debt payment to income increases the probability of denial by 60 percentage points. This is in normated probability, and that means 60 percentage points increase in the denial of the probability can be expressed in terms of percentage. So, 60 percentage points it increases for on an average per unit increase in debt payment to income ratio. Similarly, we can predict also, we can use this equation for predictions for the probability of loan denial corresponding to the PA ratio of 30%. 30% means 0.3. So, if you substitute this value 0.3 in the prediction equation, we get minus 0.080 plus 0.604 into 0.3, we get 0.101 or 10.1%. So, the denial probability could be 10.1. So, the more the percentage, more will be the denial ratio. So, this is how the models are estimated, and this is how the model can be estimated, the model can be interpreted. LOGIT model is an alternative approach to model the qualitative dependent variables, especially dichotomous or binary choice or binary response models. It avoids the unboundedness problem. It addresses the problem of unboundedness. The strategy is very simple. It takes not the probability function, actually it addresses that issue by taking the cumulative probability function, not the probability function straight. So, this cumulative probability, the di is taken as the cumulative probability, and the di is a function of the linear function of the independent variables. So, this cumulative function as a function of the linear function of the independent variables is the approach. So, this is the cumulative function, probability function, and this cumulative probability function will lie between 0 and 1. How? If the linear function of the independent variables is beta 0 plus beta 1 x 1 I plus beta 2 x 2 I plus u I is equal to minus infinity. Actually, it can take any value, there is no bound for that, it may vary between minus infinity to plus infinity theoretically. So, if you put minus for this, minus infinity for this, di is equal to 1 by 1 plus e power minus of minus infinity, that is equal to 1 by 1 plus x e power infinity, that is this is infinity, 1 by infinity is equal to 0. So, if the linear function of the independent variables is minus infinity, di is equal to 0. If it is plus infinity, right, let us see what happens. Minus 1 by 1 plus e power minus of infinity, that is equal to 1 by 1 plus e power minus infinity, that is equal to this is 0, and so 1 by 1, that is equal to 1. So, it is made bounded. The first step is it is made bounded by some link function or the cumulative probability function. So, this di will lie between 0 and 1 strictly. And now, let us see how the function, the regression function is formed. 1 by di, the 1 by di is equal to, this is the multiplicative reverse. So, 1 by di is equal to 1 plus e power minus of beta 0 plus beta 1 x 1 I plus beta 2 x 2 I plus u I. Now, we may now take this 1 this side. So, it becomes e power minus beta 0 plus beta 1 x 1 I plus beta 2 x 2 I plus u I is equal to 1 minus 1 by di. So, this is equal to 1 minus di divided by di. So, now we can again take the multiplicative inverse, we get e power plus beta 0 plus beta 1 x 1 I plus beta 2 x 2 I plus u I that is equal to the reverse, actually the multiplicative inverse, that is di by 1 minus di. Taking log both sides, we get beta 0 plus beta 1 x1I plus beta 2 x2I plus ui is equal to log anti-log. This is by natural log, we are taking both sides. So, both will get cancelled, and this is equal to log of natural log of 1 minus di by di. Taking natural log both sides, we get beta 0 plus beta 1 x1I plus beta 2 x2I plus ui equal to log of di divided by 1 minus di. Natural log means natural log is the anti-log function of anti-log function. Actually, the exponential is the anti-log function, and so the log and anti-log will get cancelled, and so you get this expression. So, now it can be written as log of di by 1 minus di is equal to beta 0 plus beta 1 x1I plus beta 2 x2I plus ui. So, this term, the expression regression expression is equal to log of di by 1 minus di. This can be by ordered like that: log of di by 1 minus di is equal to beta 0 plus beta 1 x1I plus beta 2 x2I plus ui. So, this is the regular regression formulation. Now, this di, right, is very important. Di is nothing but the probability of di taking the value 1. So, that implies 1 minus di is equal to 1 minus the probability of di taking 1, that is equal to probability of di is equal to 0, because di takes only two values, 0 and 1, and the negation of probability of di equal to 1 is the probability of di is equal to 0. So, di by 1 minus di is nothing but di is equal to probability of di is equal to 1 divided by probability of di is equal to 0. This is in literature called odds ratio. This is the odds ratio of di equal to 1. The probability of di equal to 1 divided by probability of di is equal to 0 is the odds ratio of di taking a value 1. So, log of di by 1 minus di is the log of odds ratio, that is called LOGIT. That is why this name LOGIT came. So, the LOGIT is the function of x1I and x2I, linear function of x1I and x2I. That is the logic of this LOGIT model. So, LOGIT is the log likelihood measure of di is equal to 1, anti-log of LOGIT is the odds ratio of di is equal to 1. That is that must be kept in mind. So, this LOGIT model is non-linear. You have to use maximum likelihood method. The ordinary least squares method cannot be used to estimate the coefficients, and so that must be kept in mind. Actually, your OLS will not help here. So, you have to apply maximum likelihood method. The usual t and f values, actually the derived values of chi square, are sometimes used to assess the individual and overall significance of the model. R squared is not correct measure of goodness of fit, and so some pseudo R square measures are introduced, and that are this pseudo R square measures are used instead of R square in this LOGIT model. Let us discuss about the features of LOGIT model. Actually, the signs of coefficients have the same meaning as in the linear probability model. That means the relationship between the dependent variable and the independent variables are reflected in the signs. So, the signs will give the same you can see the same kind of positive or negative relationship between both the models. Whatever sign you get for the probability linear probability model, you will have the same in the LOGIT model as well. t-test can be used for the test of significance in the LOGIT model, but the dependent variable of LPM is different from the LOGIT model. The dependent variable of LPM is the probability. Here in this LOGIT model, this is the log likelihood ratio. So, that is very important when you interpret, that is that understanding is very much important, because when you interpret the coefficients, this logic, this idea will really help. Let us take one labor force participation model. This labor force participation model is defined as the log of di by 1 minus di is equal to beta 0 plus beta 1 mi plus beta 2 si, where di is equal to 1 if the women, actually this is a women labor force participation model, di equal to 1 if ith woman decides to participate in the labor force and 0 otherwise, and mi is the marital status dummy equal to 1 if ith woman is married and 0 otherwise, that is unmarried. Si is the years of schooling. Si is the years of schooling. Now you have a kind of ANCOVA model kind of thing, and the coefficient has to be interpreted as you do in the ANOVA model. So, that has to be kept in mind, but the dependent variable here is LOGIT. Now, let us take one estimated results of the labor force participation model, and this is the result you get, and the coefficients are significant as we see in the t values, and you can see the marital status LOGIT of women participating in the labor force is negatively related. That means the married women is 1 and compared to the unmarried women. So, here they have marital status have got negative impact in the labor force participation, and years of schooling has the positive impact on the labor force participation, that is reflected in the signs of the coefficients. Now, how would you interpret this signs? How would you interpret the coefficients? This coefficient is the log likelihood measure. To get the likelihood measure, you have to take the anti-log of it, right. So, I am taking the anti-log of both the values, anti-log of the minus 2.59 and the anti-log of 0.69, that will give you the likelihood measure, the likelihood, right. So, now you can interpret how would you interpret this dummy coefficient of marital status. The likelihood of married women participating in the labor force is just 7% compared to the unmarried women. So, the likelihood of women, actually this is 0.75. So, if you take this as a percentage, this comes at around 7.5. So, it is 8% you can take. So, the likelihood of married women participating in labor force is just 7 or 8% compared to the unmarried women, holding the schooling constant. Similarly, the other coefficient can also be interpreted. On an average, 1 year additional schooling doubles the likelihood of women participation in the labor force, holding the marital status constant. So, this is how the coefficients are interpreted in the LOGIT model. We can compare the results of LPM and LOGIT for the same model. According to Emrc, he says linear probability model coefficient can be got by multiplying this LOGIT model by 0.25. So, beta hat LP is approximately equal to 0.25 times the beta coefficient of the labor force. This is this formula is except for constants. For constants, you have to do you have to add plus 0.5. So, this is the equivalence. Actually, otherwise both the models will give the same results, but this is more meaningful than the LPM models. So, the LOGIT models are very popular in the estimation of the qualitative dependent variables model. Let us wrap up what we have studied in this module. We studied linear probability model and logit models. The features and problems of these models were then discussed. The simplest possible regression model with dummy dependent variable is the linear probability model. The simplicity may not be a virtue. The LPM suffers from many estimation problems. We concluded that logit models are better than LPM. We saw how the logit models are interpreted and reported. This is the last module in the discussions on qualitative variables in regression models. With this, we conclude a discussion on qualitative variables regression model. In the next module, we are going to discuss the application of regression models for consumer and production analysis. Until we meet again, goodbye. Thank you for watching.